So we are in the middle of our discussions on free electrons. In the previous lecture, we discussed what would happen if those electrons see a magnetic field. And we observed that a new Hamiltonian could be constructed. So this is lecture number 20. And the Hamiltonian for this sea of electrons, this plasma of electrons, is given by Py square over 2m plus half m omega c square y minus y naught square plus pz square over 2m plus minus mu b p sigma z, Pauli operator. So this was our Hamiltonian. And in this Hamiltonian, with this Hamiltonian, we can find out the energy eigenstates, E. This is a harmonic oscillator. Y naught here is given by h bar kx over 2m, correct? Y naught bar is given by h by px over 2m, and this is y naught, which is the eigenvalue of y dot bar. So with this Hamiltonian, which is the Landau Hamiltonian, which we derived in the previous lecture, the energy states would be given as follows. So this is a harmonic oscillator. So the energy states are simply the energy eigenvalues for a harmonic oscillator. H bar omega c, we introduce a quantum number L, which tells you which state it is in for the harmonic oscillator. This of course represents a free particle along the z direction. So the energy associated with this term is given by h bar square kz square over 2m. This sigma z has two eigenvalues, +1 and -1. So the energy associated with this Zeeman term is minus mu b. Let's define a variable sigma, which could be +1 or -1. Or we could write plus minus mu b. So these are the energy eigenvalues, and these energy eigenvalues are characterized by a quantum number L, right? And they of course depend upon the parameters kz as well as sigma. So these are the quantized energies, semi-quantized energies in a way, because it's quantization along the xy plane. There is this free running variable along the kz. The boundary conditions impose quantization on kz nevertheless. And this is our Hamiltonian. So this is where we ended our discussion in the previous lecture. So now we would like to see what is the meaning of all of this. What does it all mean? Any questions up till this point? So remember the physical scenario. We have a metal, say, and there's a sea of electrons, and these are free electrons. They're not interacting with one another, but they are exposed to a magnetic field. What that magnetic field does is that it changes the Hamiltonian, and we went through the process of the vector potential, defining a gauge, and then looking at the Hamiltonian and seeing that it resembles the Hamiltonian for a harmonic oscillator, and then we come up with this revised Hamiltonian with this eigenstructure. Now in this Hamiltonian as well as in this eigenstructure, you notice that there is no kx or ky. There is only a kz. Now this is a three-dimensional solid, and the same description also applies to a two-dimensional solid. But nevertheless, let's see how the K structure is modified, how the reciprocal structure is modified. So if you have a three-dimensional solid and you have electrons there, in the K space, the electrons occupy modes which are equidistantly spaced on the reciprocal lattice. So in the absence of a magnetic field, you have a Kx, Ky, and Kz, and you have all of these points equidistantly spaced So you have a net at a certain value of Kz, then you have another net, so you have this three-dimensional structure of equidistantly spaced K points, correct? So this is all that we know, but this is in the absence of a magnetic field. Now the K structure has really been modified inside the presence of a magnetic field. Now if I were to draw the K structure, first of all, just suppose this is Kx and this is Ky, and I am looking down the Kz direction. So previously what we had were equidistant points equally spaced cubes in the three-dimensional structure and squares in the two-dimensional net, right? So all of these points are modes that are available to the electrons, and they will gradually occupy these modes until the Fermi surface is reached, right? So this is a structure in the absence of a magnetic field. Now if you observe either the Hamiltonian or the energy level structure here, you do not see any Kx or Ky dependence. You only see a Kz dependence. So the Kz dependence remains unchanged. In the absence of a magnetic field, we do know that our Hamiltonian is simply Px square plus Py square plus Pz square minus mu b b sigma z, right? So this is the Hamiltonian in the absence of a magnetic field, and the K structure would be all the K points that are conventionally drawn. But now here you see that there is no Kx or Ky that you observe. What has happened is that all the Kx and the Ky points, they redistribute themselves into a new structure in the xy plane. And when I say the xy plane, I mean the Kx Ky plane. They redistribute themselves. All of these modes they do a choreography and they reorient themselves so that they are now defined by a single variable, which is L, which could be the radius of a circle, correct? So what's happening in the presence of a magnetic field is that this nice regular periodic arrangement of points in the xy plane is now redistributed, and you will form rings inside the Kx Ky plane. So you will get a series of rings. And all the points that were prior to the application of a magnetic field lying at the intersection of this regular periodic grid would now redistribute themselves so that all of these points are now located on one of these rings. Okay. Now, in fact, the number of these rings is very large. and you can do a calculation, a back of the envelope calculation on how many rings will be produced. But since the number of points is very large, because the number of electrons is very large, the number of these rings is also very large. Okay, so all of these points now redistribute themselves onto the ring. And now if I were to draw this k-space structure in 3D, because I have to take care of the kz dimension as well, what would that structure look like? That structure would look like a series of concentric tubes. Those tubes are called Landau tubes. Now the k-space structure in the presence of the magnetic field is now modified. Now I draw a perspective view of this k-space picture. I will get these tubes. So this is my kx axis, my ky axis, this is my kz axis, and here is my Fermi sphere. Assume this is a sphere. Okay, so this is now what the new structure looks like. This is emblematic of Landau quantization. These tubes are called Landau tubes. So if I look at these tubes from a perspective, from a side, they are elongated tubes, and all the points in the k space that lie inside the Fermi sphere, because at 0 kelvins only the points inside the Fermi sphere are populated. The Fermi sphere is the boundary between occupied and unoccupied. So all those points that lie inside the Fermi sphere, they redistribute themselves on these tubes. And each of these tubes, in fact I've only drawn a handful of these tubes will be in the thousands, tens of thousands, okay? And these tubes are denoted or signified by the quantum number L. So this is the L equals 0 Landau tube. This is the L equals 1 Landau tube, the L equals 2 Landau tube, the L equals 3 Landau tube. And there is a maximum number of L which would be allowed depending upon the density of that substance, depending upon the volume and the number of electrons that are present. So L is a quantum number that really goes up to infinity, but it is bounded on the upper side by the Fermi sphere. All right, and we also looked in the previous lecture that of course there is going to be a certain number of points. So a large number of points in the kx ky plane, they coalesce onto a Landau tube, they succumb to a Landau tube, they kind of stick to a Landau tube, and the number of points associated with each Landau tube is, so many points they cling to a Landau tube, and the number of those points we already determined in the previous lecture. That number of points on a particular Landau tube, let's call it NL. In the last leg of the previous lecture, we found out that this number was 2 times phi over phi naught, where phi is the flux through the material. So the field is along the z direction, so this is the flux through the material. A is the cross-sectional area of this material, and phi naught is a constant that is given by h over E. H is the Planck constant, E is the charge on an electron. So this is something we derived in the previous lecture. So this number of points in the kx ky plane belong to each Landau tube at a particular section, but then you have these many sections. So if I drew a section perpendicular to the kz direction, this number of points will cling to each of the Landau tubes. All right, and this is something that we derived in the previous lecture. And in the homework, I'll ask you for an alternative definition of this number. So this is like a degeneracy. This factor represents a degeneracy in the kx ky plane. So this many modes exist on a Landau tube on a section perpendicular to the kz axis. And higher the number of, okay, first of all, one small digression, this phi naught, okay, just a minute, this phi naught is a constant h over e. It has a certain value and it has dimensions of flux Weber per meter. So it's just like a fundamental constant. Just like we talk about the charge and electron, the Planck constant, this is also a fundamental constant, similar to the fine structure constant. So this is the unit of flux. This is the smallest flux that you can ever get. Flux also becomes quantized, especially when you talk about superconducting circuits and quantum computing with superconductors. Those Josephson junctions that work with flux, they see flux being quantized in units of h over e. So this h over e is also called the fluxon. So phi naught h over e is the fluxon. Okay, so this number of points cling to each Landau tube in a section in the kx ky plane. Yes, Dua, what was your question? So there are a large number of points in the kx ky plane, but those points are now, they fall onto one of these tubes. So each of these tubes has a large number of points. The number of points on each tube, on each circle rather, is given by this. Okay. Now if I were to increase the magnetic field, what would happen? The number of points on each tube will go up. But what's going to happen to the spacing between these tubes?
The points are less, like spacing कम हो जाएगी.
क्यों?
क्योंकि आप और points ला रहे हैं different value है ना.
Okay, so let's look at this question in another light. Suppose I were to draw a diagram. So this is kz and this is energy. This energy over here, EL kz, EL kz. I'm ignoring the spin for a minute. Remember that along the longitudinal direction, along the z direction, you have many points along the z direction, and those points are quantized along the z direction as well because of the boundary conditions. So each of these z tubes, so if I were to draw a picture of each z tube, just one Landau tube here, so this has a large number of points. Okay, and in fact the because of the degeneracy along the kx ky direction, I can't really draw the discrete points along the azimuthal direction. So there's a large number of rings in fact, and these rings are separated, and this separation is delta kz, which is inversely proportional to the length of the sample along the z direction, right? So this delta kz is 2 pi over Lz. So all of the points in the three-dimensional sphere, they kind of coalesce into rings, and those rings all together, when they are strung together, they form a tube. Ring है एक, फिर एक ring है, फिर अगला ring है एक, ये बहुत से rings मिलकर एक Landau tube बना रहे हैं. Yes.
Spacing, can you mean spacing between the rings that make up one Landau tube, not the spacing between?
No, I'm talking about this spacing from here to here, this spacing,
Spacing between Landau.
right? So this is a radius, right? And this radius is, say, let's call this radius KL. This radius is ignorant. This radius is KL plus 1. So if I were to draw the area between these rings in the kx ky plane, I will get pi KL plus 1 whole square minus pi KL square. So I've defined this new wave number KL. So I can immediately determine how many points exist. All the points that exist between these two rings will coalesce onto the Landau tubes, onto either of these Landau tubes. So the number of modes will not change because the size of the sample is not changing. The number of electrons is not really changing. You're not injecting electrons or taking out electrons, or the size is not changing. So the number of modes, total number of modes remains fixed. They just redistribute themselves. Okay. Now what I would like you to appreciate is that if I were to draw a graph between EL and KZ, if I look at my dispersion relationship, what kind of graph would this be? It will be a parabola. So this will be a parabola. This is a parabola for some L. Let's call this L0. So as Kz changes, so it's a parabolic function of Kz. So for L equals 0, this is the parabola. For another L, which is the next Landau tube, this diagram will look like this. And the spacing between these levels, between any 2 points with the same Kz, is simply h bar omega c. That's the Landau quantization that we are observing. So you will get, if we were to draw a diagram of the energy versus Kz, you will get the sequence of parabolas. So this is, so first of all, I did explain to you how the K structure is modified. Now I'm kind of piercing into the energy manifold, what the energy diagrams look like. All right, so this is the new dispersion relationship when the energy is plotted with respect to one of the variables Kz. And do remember that there is always going to be a Fermi energy, maximum energy, EF. And we'll show later that this Fermi energy will also depend upon the magnetic field. But for a time being, just assume that there is an upper limit to the energy. So the number of levels, the electrons are going to fill up these levels, right? So there will be electrons on each of these Landau tubes, and they will fill up successively as the energy is built up. But all the levels up till the Fermi energy will be filled. Okay. Now there is, this Fermi energy really depends upon the number density of electrons. How many electrons exist per unit volume? For a rarer solid, this will come down. This depends upon the size of the material and the density, the number of electrons that are available. Right? Remember that this Fermi energy is 6 pi square n over raised to power 1 over 3 for a 3-dimensional solid. So, so this is what the structure looks like. Now this omega c, we do know, is equal to, it's the cyclotron frequency EB over m. Now if I were to increase the magnetic field, what's going to happen to these Landau levels? They're going to kind of be dilated, they're going to be further and further apart. So when that happens, the maximum L that can be accommodated within the same Fermi energy is going to drop. Fewer Landau tubes will now fit inside the Fermi sphere. So if I were to draw this diagrammatically in terms of the K-space structure, let me first draw the Fermi sphere, and let me draw the same Fermi sphere again. Okay, at smaller fields, I will have a particular number of Landau tubes fit inside the Fermi sphere. Remember that I'm just for pedagogical purposes drawing these a very small number or handful number of tubes, but the number of tubes is really maybe in the tens of thousands. Now if I were to increase the magnetic field, the spacing between these levels goes up because omega c goes up. For higher magnetic fields now, a smaller number of Landau tubes will fit into the Fermi sphere. So I might drawn in a really exaggerated sense. I might have just a smaller number of tubes fit into the Fermi sphere. But the number of points that are now going to coalesce onto each of these tubes is going to readjust itself. And that can be seen here. If B goes up, the degeneracy of each of these Landau tubes goes up. So two effects really happen. One is that this degeneracy changes. The second effect is that the Fermi sphere also changes. It can compress or expand a little bit, as we will see in a minute. Okay, so I've kind of started off with the Hamiltonian, looked at the energy dispersion relationship, given you a Landau tubes view in the K space, then presented to you a dispersion relationship, a plot of the energy versus Kz. Another way to kind of visualize everything that is happening is that if this is my energy axis and I plot a magnetic field here, so up till 0 fields, all the levels up till EF are filled. Now if I were to increase the magnetic field, all of these energy levels, remember that these energy levels are really finely spaced quantized levels because of the periodic boundary condition of the solid. K space is quantized. Now what's going to happen is that if I were to increase the field, suppose the field is drawn in a piecewise continuous fashion, so the field is some value, non-zero value here, B1 greater than 0 in this region. What's going to happen to the energy manifold? All of these levels are now going to coalesce onto the Landau levels, which are characterized by L values. So all of this is now going to project itself onto these discrete levels, the Landau levels, because of the quantization. Those Landau levels are simply these Landau tubes. In K space, they are simply these parabolas when viewed as a dispersion relationship of this kind. Okay. Now all of these modes are going to fall onto one of these levels. Total number of modes is not going to change. If in another region I kind of increase the magnetic field B2 larger than B1, then these level spacing is going to go up. So I will have fewer Landau levels now. Probably just this. Now all of these electrons are now going to redistribute themselves onto these Landau levels. The degeneracy of each level goes up. correct? And what's the role of this last term, the spin term? Mu b is a small number, it's the Bohr magneton, E h bar over 2 times the mass of the electron. So what this spin term does, so to each Landau level, any guesses? What's the role of this extra perturbation to the energy? What's the role of the last term? How is it going to change this energy level structure? शिफ्ट कर देगा? नहीं, क्या करेगा? Split कर देगा. So suppose I look at the impact of spin onto this diagram. It's just going to split this up into two finely spaced levels. With one, whatever this energy is, which is whatever it is. So this diagram is drawn at some fixed value of kz. Some fixed value of kz. So whatever this energy is, which is h bar omega c, L is 3 plus 1 half plus h bar square kz square over 2m. This is the energy of this level. Now this level is going to be this energy plus mu bb. And this level is going to be this energy minus mu bb. So just slightly splits each level, G. This one. So this energy is h bar omega c. L is 3 here, so 3 plus 1 half plus the kz term, which is h bar square kz square over 2m, whatever kz is for this diagram. Now this level is split, further split because of the spin. And this energy due to the spin, the magnetic energy, the Zeeman energy is plus mu bb or minus mu bb. So these are the two levels over here. Now you could do an experiment in which you kind of make transitions between these Landau levels. Okay, so there will be a certain energy gap between these levels. That energy gap depends upon the magnetic field. It could be in the RF regime, it could be in the microwave regime. You can do transitions between these Zeeman levels as well. So this energy structure is built up for these free electrons when they see the magnetic field. So this is the quantization that I wanted to talk about. Now we're going to look at some of the ramifications of this Landau quantization. We're going to explore two effects, but let me take a question. Yes. क्योंकि वो स्प्लिट इसलिए हो रहा है क्योंकि हमारे हैमिल्टोनियन के अंदर ये एक हैमिल्टोनियन है सिग्मा z. This is Pauli operator. When you place a spin inside a magnetic field, this is the Hamiltonian. The energy values of this Hamiltonian will correspond to the eigenvalues of the Pauli operator, which is plus 1 and minus 1. So two energy levels are created, or the qubit is created. One with the energy mu bb plus 1 and the one with the negative sign. So that's why these two levels are created. This effect is called the Zeeman effect. Any questions? More questions? Because things are going to get slightly, if you don't understand this, you'll be wasting another day and a half. We won't be able to understand anything. Any more questions about this? Yes.
Sir, just to clarify, अगर हम Landau rings में spacing कम करें तो हमारे number of modes बढ़ने चाहिए.
Spacing कम करें यानी magnetic field हम कम कर रहे हैं.
Modes बढ़ने चाहिए.
Why? कम हो जाएगा ना. The number of points, the degeneracy of each Landau tube is going to go down. So you will have more Landau tubes inside the Fermi sphere, but the number of points that cling to each Landau tube is going to go down. So now there's a fine balance. When you change the magnetic field, two things happen. First of all, the spacing between the Landau levels changes. Right? So this spacing changes. These Landau tubes kind of expand. They become rarer. The second thing is that the Fermi level may also change. So now we would like to explore both of these effects. But in order to explore these effects, we want to find out the density of states. So the density of states, what is the density of states? What's a broad definition of the density of states? What is meant by the density of states? So dE, the number of states per unit energy, right? So that's the density of states. And we do know the density of states for solids in the absence of magnetic fields. Okay, so let's do a quick recap. If I were to draw the density of states for solids, so this is my E here. I have the density of states here in each of these y-axes. And this is 3D solid, this is a 2D solid, this is a 1D solid. What will the density of states look like? 3D में क्या होगा? नहीं, 3D में upward positive curve proportional to square root of E. This is something you should be able to, if there's one lesson that you want to walk away from this course, is what the density of states look like. Because once you have the density of states and the Fermi-Dirac distribution function, you can find out physical parameters. So what about a 2D solid? It's just independent of energy. And a 1D solid, just a chain, it just comes down as the reciprocal of the square root, like this. So this is something you need to remember. Now you can derive these density of states, and you have done, I think, homework problems related to this. There was a question in the midterm as well. Ananta, were you able to do any tutorial last week and go through the midterm? So you're able to derive these density of states from first principle. Now another way of deriving the density of states, let me kind of propose to you. If you would look at this 3D solid, suppose there is no magnetic field. The 3D solid has some structure in K space. So the the density of states dE really comes from GK, density of states in the K space, and the dispersion relationship. So for a nice periodic regular K space structure, which is existent for a solid in the absence of magnetic field, everything is equally spaced. You can look at the density of states in 2D and then convolve it with the density of states in the third dimension. So convolution, you've already seen what it means. So if I were to take the 2D density of states and convolve it with a 1D density of states. So the 2D structure is a net in the horizontal plane. And these are your K space points, right? Equally spaced. This is the Kx, Ky plane. If you take the convolution of this K space structure with the third dimension, which is just one dimension, a string of points, I would get the three-dimensional K space. So, and the density of states of this structure and the density of states of this structure can also be found through convolution. All right. Now the point is that, okay, let's check if I get this relationship through a convolution of of the regular density of states. Suppose this is some constant. Let me call this constant A. It's independent of energy. Convolution with B, right? So I need to find out the convolution of these two functions. A and B are constants. So from the definition of convolution, I construct an integral. This is the very definition of convolution. I form a convolution integral. And for that, I just take out the constants A, B, integral. Now, one of the functions which is independent, I need an integral over some variable, let's call it E prime. And I change this E to E prime, put a minus sign with it, add to this E, because I want to find out the final function that I want to find out is a function of E. So this E I put here. The other E's I put as a running variable. Okay, and there's a minus 1/2 already here. And I take the integral from 0 to this E. So this is how I construct a convolution integral. So I take one function, I take the other function, invert it, and translate this by a variable in whose domain I want to find out the convolution integral. So I want to find out the convolution integral as a function of E, so I put E here and I change this variable to some other variable, E prime or X or Y or anything. And that's how I form the convolution integral. So if I were to do this integral between a 1D and a 2D density of states function, let's see what the result is going to look like. AB. Now this is an integral E minus E prime. So what I could do is simply put a minus sign here, E minus E prime minus half plus half becomes 1/2, 1/2, correct? Minus 2AB. When E prime is E, this becomes 0. When E prime is 0, this becomes, so I do get some constant and the desired functional form. So it works. So whenever I want to construct a 3-dimensional density of states, either I could start from first principles as you've done in your homework, but I could also look at the 2-dimensional density of states and the 1-dimensional density of states and convolve the two functions. Now this is really useful in our context today, because in our context the 1D density of states hasn't changed. It's still the same in the Landau quantization picture. It's only that the 2-dimensional density of states is now different. Okay, so now we want to find out the density of states in the presence of a magnetic field. We use exactly the same argument. In the presence of a magnetic field. Let's call this D in the presence of a magnetic field E, right? So what I need to construct is, once again, I need a 1-dimensional density of states, which is still the same as before, because the Z structure hasn't changed. Some constant, okay, I don't want to use the word beta here, B here, because it now represents a magnetic field. Let me use something else. All this, say beta. Now what about the 2-dimensional density of states? What should I write for the 2-dimensional density of states? What does it look like? And the answer actually lies here, and it lies here as well. First of all, do remember that the L equals 0 state does not start at 0 energy. It starts at h bar omega c over 2 when L is 0, plus of course h bar square kz square over 2m. Whatever kz we're talking about. Kz could be 0, could be anything. So it doesn't start off at 0. That's the 0 point Landau energy, the 0 point quantum. Now, by looking at this figure, so this lower level is not 0, it's really some small h bar omega c over 2. What should be the two-dimensional density of states in the presence of a magnetic field? What should it mathematically look like? Equally spaced levels हैं, quantized levels हैं. क्या इसके mathematical structure क्या होगा? Linear? कौन सा फंक्शन है जो रिप्रेजेंट कर सकता है इस इक्वली स्पेस्ड लेवल्स को? स्टेप फंक्शन. हमने वो क्रिस्टलोग्राफी में भी ऐसे फंक्शंस देखे हैं, कॉन्वोल्यूशन. ड्रैग डेल्टा फंक्शन, अ ट्रेन ऑफ ड्रैग डेल्टा फंक्शंस, राइट? So if I were to write this train over here, so I will write a drag delta function E minus, and what's the energy? H bar omega c L plus half okay, let me, I need more blackboard for this, so let me write this again. E3D in the presence of a magnetic field as a function of E is now a Dirac delta function E minus h bar omega c L plus half. So it's a train of Dirac delta functions. This is energy. So here the energy is, so if I plot the energy in units of h bar omega c, this is 1/2, this is 3/2, 5/2, 7/2, and so on. Correct? And the degeneracy of each of these levels would be the strength of each Dirac delta function, NL, which I've written over there, NL, which will depend upon the magnetic field, NL. And I can spell out NL 2 times phi B A H E. Sum over, so this is the strength of each of these Dirac delta functions, which is the degeneracy that we've calculated, including the spin factor. This too comes from including the spin factor. And it depends upon the magnetic field. So this is proportional to omega c.
तो NL वाला फैक्टर
ये NL ही है, right? So if I put m here and m here, this EB over m is omega c. So this becomes m omega c, proportional to m omega c. So this is a factor proportional to m omega c. So, and I want to take the sum over L's. Now this L starts off from 0, but it doesn't go all the way up till infinity. It goes up to some maximum L, which is determined by the size of the Fermi sphere, L max. And I want to take the convolution of this thing with some constant beta, which you've already calculated in your prior lectures. I will write this down and E minus half. Okay, so this is the three-dimensional density of states that we need to calculate. And we can calculate it. Yes, please. You have a constant? So this is a Dirac delta function, but it has some strength. That strength is the degeneracy. How many modes exist at that energy level? So you just put in that number over here. ये number, ये वाला number है. ठीक है? Now if I want to calculate this, I can write this as m 2m omega c 2 pi h bar. Let me write this number in this omega c form. L, go from 0 to L max. Now let me write down the integral. The convolution is an integral, right? So 0 to E, this E over here, dE prime delta. I replace this E with E prime minus h bar omega c L plus half. Put this beta out here, it's constant. I replace this E with minus E prime and put an E minus E prime minus half. Correct? So I need to furnish this Dirac delta, this integral. Now I just use the sampling theorem here. This is non-zero only when E prime equals this. Okay? So if I were to do that, this becomes m omega c pi h bar beta. L goes from 0 to L max. I just take this into the denominator 1 over, I need to replace this E prime with this thing, E minus h bar omega c L plus half square root. So this is my density of states in 3 dimensions. In the presence of a magnetic field. Now what is L max? L max is such that L max is the maximum value of L such that h bar omega c L max plus half is less than or equal to EF, right? So this is how we define L max. Now these two equations together help us determine the density of states in 3 dimensions. And we can plot this. By the way, one thing I would like to, in condensed matter physics, whenever you do these quantum calculations in condensed matter physics, do notice that this E has to be greater than h bar omega c for this to work. Because the argument of the square root has to be positive. Otherwise everything breaks down. So a constraint that when we program this and we want to find out what the plots look like, we really have to ensure that the energy that we're talking about is greater than h bar omega c over A. And a function that achieves this is called the Heaviside function. The Heaviside function is a function is some function of x which is 1 if x is positive and 0 if x is negative. This is called the Heaviside function or unit step function. So when I program, I kind of make sure that I only take positive values in the square root. So now I can actually find this out. One thing I do notice that when I want to program this, I want to find out what the density of states looks like. I can do a substitution. I can express my energies in dimensionless variables. That's always easy to do. So I take each of the energies and divide by h bar omega c. So this calculation is done at a fixed magnetic field. Fixed magnetic field, fixed omega c, fixed cyclotron frequency. So I take every energy and divide it by that h bar omega c. So I define E over h bar omega c as my variable x, as a new variable x. So I can recast everything in terms of x instead of E. I can also define EF h bar omega c as x naught. Remember, when I just write EF, just EF bare EF, it's the Fermi energy in the absence of a magnetic field. The Fermi energy in the presence of a magnetic field does change. Keep that in mind. So when I do all of these substitutions, I can write my dx in the presence of a magnetic field as, let me write down what I get. So this is the density of states, though this density of states in the presence of a magnetic field is exactly equal to the boxed expression that I've written over there. All right, just a matter of substitution. This should be homework problem, Anamta. And in the absence of a magnetic field, I do already know what the density of states is. In the absence of a magnetic field, zero field, dx is given by def x naught x. This is something you can also prove. This is the density of states in 3 dimensions. Look, this is square root of energy. Exactly this thing. So this is the density of states in the absence of a field, the density of states in the presence of a magnetic field. Let's try to plot this density of states. We know what this density of states looks like already. Let's draw a big graph here. Energy and some density of states, right? dx. So instead of E, I'm plotting with respect to x, which is just a rescaled energy. So what should a plot of this look like? right? Square root function. What should this look like? So everything is similar here. This term is similar, this denominator is similar, there's only a 1/2 factor, but now we take a sum over L maxes of over these reciprocal of square roots, ensuring that this remains positive. So let me show you what this plot looks like. So it's as x goes up, it's going to go down. When x equals that singularity point L plus half, it's very high. So it's like a peak. It should be really like a peak. So if this is my x, here is 1/2. So the first peak must occur here, and then it must go down. The second peak must occur when x equals 3/2, which is the value with L equals 1. So the second peak hypothetically must go like this, right? So the density of states should now be, these not Dirac delta functions but peaks riding on top of the three-dimensional structure. Let's see if that is really the case. Okay, so first of all, I've plotted just the raw density of states in 3 dimensions, square root function. Then I plot the density of states in 3D in the presence of a magnetic field for different values of L. I take I need a sum. So I sum over L equals 0, L equals 1 up till L equals 9 just to see what it looks like. I take that sum and plot it. And if you notice here, I also multiply each term with the Heaviside function, ensuring that the argument remains positive. So, pointer la sakte hain? So this is what it really looks like. And now I juxtapose the two together. Indeed, this is my observed structure. So I have this density of states in 3D. MATLAB Mathematica is not plotting the continuous time, so it really goes up to a large value, drops down and goes up back to the large value at these ladder points. So this is, notice, this is happening at 1.5, 2.5, 3.5 and so on. Okay, so this is what the density of states looks like in the presence of a magnetic field. Now the density of states has this discontinuous structure. It's striated, it is discontinuous. Now what implications does this density of states have for physically realizable properties like conductivity, like magnetization, like heat capacities, like total energies? Of course it's going to have an impact on all of these physically realizable parameters. So what do you think should our next step? Suppose we want to find out the total energy of the system. What should be the next steps be? First of all, we've seen how the density of states changes with the field. But the question is, does the Fermi energy also change with the application of the magnetic field? So that is a question we're going to explore in our next class, and then we're going to look at how these properties manifest themselves in the presence of a magnetic field. So now you have a sea of electrons, they're inside a magnetic field. How does it impact the heat capacity for those electrons? How does it impact the susceptibility for those electrons? How does it impact the conductivity? If you want to do theoretical condensed matter physics as your favorite pastime, this is the starting point for all of these quantum effects in two-dimensional solids. Quantum Hall effect, spin Hall effect, fractional quantum Hall effect all start from this Landau quantization. Okay, so in the next lecture, which is tomorrow 5 p.m. Wednesday, April 2026, 5 p.m. same place, we'll meet for another hour and a half probably and discuss